Okay, so suppose you had a differential equation that looked like 2xy dx plus x squared dy is 0. Please note, the dx and the dy being separated from one another like this is a real clue that someone wants you to either think exactness or they want you to think, what's the other thing where I separate?
Separation of variables.
Yeah, separation of variables, right? So either they want you to think, dude, this equation's exact, or they want you to think, hey, this is separable and I separated it for you. Or they want you to think, haha, I tricked you. Right? I don't tend to do that, for the record. So, I don't really have a way to test whether something's exact or not. That would be a nice tool for me to have. But I don't. So maybe I'll just try this. So what do I need 2xy to be?
The f partial, or the x partial.
Yeah, I need this thing to be like fx for something, right? Yeah. I need x squared to be fy of something. Okay, so how do you find something that's got an x partial of 2xy?
2y?
What did you differentiate with to get fx? With respect to get fx? You differentiated with respect to x, right? So you would like to undifferentiate with respect to x. And so you got 2xy, and you're trying to integrate dx. Right? This is like kind of morally f should be this. Okay, so I get x squared y plus something that's constant with respect to x, which means it could be a function of y. Or just a number. You guys cool with that? Okay. If fy is x squared, what does that mean? That means that f should be the antiderivative of x squared with respect to y. Right? Out of which you get x squared y plus something that's constant with respect to y, which might be a constant, obviously a different constant function of x. And then you need to play mix and match between these. How hard is mix and matching between these? Not very. X squared y matches with x squared y. And your constant function of y has to be
Constant in x.
also constant in x. You guys see that? So your constant function should just be a actually constant. So what I think I found is that f of x and y has to be x squared y plus some constant. And then what am I doing with this?
Can I ask what the hat is?
Yeah.
Okay.
I didn't want to confuse it with this one, but I still wanted to use a k.
Okay.
K1 and K2, who cares? Decorate somehow so they're not the same.
Its solution is f of x and y equal to constant, so you can just solve for constant. Or, yeah,
So
just gonna make it
your solution for an exact equation is the f that you got set equal to some constant.
Right.
Which means that you probably don't really need the constant of integration here.
We can just blend it to the other one.
Yeah, you can just blend it to the other one. So my solution is going to look like f of x and y is x squared y plus c equals some other c. So maybe c1 and c2, right? And you don't really need to label it f of x and y because who cares? Right? And you don't need both constants because you subtract one to the other side and blend them together.
Now, what if it was instead of like ky and kx being equal to each other, if it was something else? You said it could end up being a function instead of a constant. What would that look like?
I'll show you in a bit. that would look like maybe this one got x squared. Never mind, I'll show you now. That would look like maybe this one out of the integration. You got like x squared y plus y squared plus some constant, some function of x. And then out of this one, you get the same thing you got. So you take this constant, this function of y and that function of y and say, okay, those match up. And then this other thing can be the constant of integration. There's no extra x's kicking around here, so I don't need them. You might not be able to do this reconciliation. You guys remember that from finding potential functions? Like sometimes there wasn't a potential function. What's up?
If we do have that example right there where we have the extra y squared, what is our f of x y then?
That'll get a y squared in it.
Oh, that's it.
Yep. Yeah, you'll just take the thing that matched and put it in.
We got something of that form on, say, test, and we decided to divide everything by x dx and solve it normally.
Sure, have at it.
Okay.
So this thing does some stuff that you won't be able to do that way, right? That when you like rearrange algebraically, you won't get something convenient that's form you know. Then you might want to think about this. But if you can rearrange this into a form you already know, hit it.
Like this form covers separable things, but also other things.
Yeah, this thing will cover some things that are separable. It'll cover some things that you can rearrange to be linear. It'll cover some of everything essentially, but it'll also cover some like really nasty nonlinear stuff. Okay, cool. Does that make sense? So what is my final solution here? Like, what is the actual solution to this thing?
X squared y equals c.
Yeah, x squared y is c, which you can solve for y. Right, so your actual honest-to-God solution might be c over x squared, which is exactly what you'd get out of rearranging appropriately.
If you did it separately.
Yeah, if you did it a different way.
What's interesting is
Cool.
that x cannot be 0.
Yeah, and x can't be 0, clearly. Because if
that
x
would be
is-
a trivial solution.
Yeah, if x is 0, then you're looking at the trivial solution. So, question. What would a test for exactness look like?
The x solution and the y solution have to be the same.
Okay, so no. Yeah, it would sort of look like those two pieces have to be reconcilable. Yeah, that's true. There's one that I think is maybe easier to remember. So the test for exactness, exactness. I want you to think Claros.
Oh.
Does anybody remember Claros?
Oh, yeah.
Oh yeah?
Equality of mixed partials. Theorem.
Yeah, Claros really says fxy is fyx, right?
Yeah. They're continuous.
And if that holds, then there's a gradient of some function.
So this is like, is this function kind of continuous enough to be dealt with, right?
Yeah.
Okay, so I would like for this whole thing to work, right? This whole thing working really just depends on f being nice enough, right? So if f is nice enough, then Claros is true. So I should just check if Claros is true, and that's probably enough to know that it's nice. You guys see that? So the test for exactness is m of x and y dx plus n of x and y dy equals 0 is exact if m, let's see, m was the x one already, so I should take the y partial, and then I should set that equal to n with respect to x, right? If I take the cross partials and they're equal, and I'd like them to be equal on some rectangle, right? And I probably should toss in one more thing here. What else should I toss in? Oh, I should definitely toss in an if and only if. And then I should also toss in well, at least that m and n need to have derivatives. Should probably assume that n and m have continuous derivatives.
So they have to be continuous on that rectangle as well.
Yeah. On some rectangle R. Is that making sense? So if you take the mixed partials, set them equal to each other, and see that they're actually equal, sorry, that was weird. If you take the mixed partials and notice that they're equal to each other, then you can proceed with the idea of finding kind of an antiderivative that'll be the solution to your exact equation. Cool? If you can't do this, don't bother. So that's what the whole first mess of things in 2.5 are, just like test to see if things are exact. If they are exact, solve them. Cool? Questions, thanks?